we have to analyze the algorithm asymptotically. We need to see that which algorithm is fast asymptotically and which is not fast. So the intuition of asymptotic analysis is that we are working on the sufficiently large value of n, and for the large value of n, we need to see that which algorithm will run fast and which algorithm will run which algorithm will run slow. While we are going to do the asymptotic analysis, we need to use the asymptotic notations actually. So we have the asymptotic notations, and with the help of the asymptotic notation, actually, you need to represent the complexity in the terms of the asymptotic notation. So we have the 5 notation here. So see that with the help of these 5 notation, we analyze the algorithms, and we can represent the complexity of any algorithm with the help of these notations. And now actually for every notation we have some different intuitions, and without using the modifier, if you are just using those notations, then every time if you are going to use the O notation, it has some different kind of notation and meaning. If you are going to use the big omega notation, then it has some different intuition. Big theta has some different intuitions, and small o and small omega also having the different intuitions. So so these are the 5 notations we need to use for denoting the analysis. Like in earlier we have seen that the algorithm A requires, we have seen that algorithm A requires 1 by 2 n square minus half of the n. And this also we have seen in this case of the insertion sort. And say you have the insertion sort algorithm, okay. And in insertion sort algorithms, we know we have the counted the operations, you know that, and the operations comes in this. So actually for denoting the complexity of your insertion sort, we just not use this kind of equation. You simply say that the insertion sort will take the time, say we can order of n square, and this is what, this is the big O of n square. So once I am going to say that big O of n square, so I have some different mindset of it, has some different meanings actually. Once you are going to use the big O notation, it has some different intuition. If you are saying that the algorithm has big omega n square, big omega of n square, then it has some different intuition. If you say that you have the big theta of n square, it has some different intuition. So every notation has some different intuitions once you are going to use, and that actually you need to know before you are going to represent these notation when you are going to analyze the algorithms. So let us see one by one. We have the notation, we are going to see one by one. So let us see first simplest one. So first we can discuss like this big O notation, okay, and we denote by writing capital O. This is the big O notation. Intuition of this big O notation is it denotes the asymptotic upper bound that may or may not be tight. We will see may or may not tight. I will discuss it later on. So asymptotic upper bound, because we are using the asymptotic notation and we are analyzing the algorithm asymptotically. We are going to select the algorithm asymptotically, means for sufficiently large value of n, we need to provide the analysis of your algorithm. So the notion of asymptotic upper bound means you are denoting the worst case of your algorithm. Like you have the, say you are having the n, and for irrespective of the n, you have said this is the upper bound of your algorithm, means this is the time of your algorithm, this is the time, means your algorithm, this is the upper bound you have set. If you have set the upper bound, okay, means this is the maximum time, whatever be the input, your algorithm, irrespective of the input, your algorithm will not take more than this time. And sometimes your algorithm may require this time, sometimes it may require this time, sometimes it may require, for some input it may require this time, like that. But your algorithm will not take time more than this. So this is the upper case of your algorithm. So whenever we are going to use the asymptotic big O notation, then big O notation denotes the worst case of your algorithm. And what is your claim? Your claim while denoting the analysis with the help of O notation, you are claiming that this is the maximum time of your algorithm takes. Means your claim is that this is the upper bound. Means your whatever input you can supply, the algorithm will not take time more than this. So okay. So when we have the, say you have the, we have some algorithms A, and A requires time. Say for example, you come to know that we have some sort of polynomial. A requires time 5 n square plus 10. So this is the number of operations required by the algorithm A. So we assume this is the f of n. We say this is f of n. F of n is 5n square plus 10. So the number of operations required by your algorithm is 5n square plus 10, and we are denoting by writing f of n. So here you have the f of n. F of n is 5n square plus 10. This is the time. So how you can represent with the help of asymptotic notation? If you come to you and during the computation of the number of operations, you come up with this kind of equation. So you have the equation like this: f of n is 5n square plus 10, and we need to represent this in with the help of the big O notation. So how we can represent with the help of big O notation? We need to see. So see, you say that f of n, we are writing like this: f of n is big O of g of n. So this we are using the big O notation, and you can say that f of n is big O of g of n. So f of n is this. You have the analyze the algorithms, and you have the number of operations. Means you need to determine the function g of n that you are going to bound this function. Means you say that you need to determine the g of n so that you can say that f of n is big O of g of n. Means if and only if, how you will able to say it like this: if and only if there exist positive constants, say c and n zeros, such that f of n is less than or equal to some c into g of n, like this. So if you are meeting this condition, so you need to compare the, you need to represent in terms of the big O notation. So if you say that f of n is big O of g of n, then you must satisfy this kind of, and this is for every value of n greater than or equal to n0. And the n0, you know that this is the break-even point. You come to know that after the value of n0, the rate of growth of algorithm, the rate of growth of the function f of n is less than or equal to the rate of growth of the function g of n with some constant multiplier. So after the value of n0, this relationship holds true. This means actually you are saying like this. So you have some, say for example, this is having the, say, some c into g of n, okay, some c into g of n, and you may have like this situation, and this is the value of your n0. So this is n0, and this is what? This is f of n. This is n, and this is the number of operations. So you can come to, you say that f of n, the rate of after the value of n0, after the value of n0, the rate of growth of f of n is same or less as compared with the c times g of n. Means you are claiming that this is the, that's why I'm saying that big O notation represent the asymptotic upper bound. Means this is the upper bound you are mentioning, that whatever be the value of n, your rate of growth of f of n will not be more than the rate of growth of c into g of n. So that's why this denotes the upper bound. So once you say that f of n is big O of n is g of n, this means you are denoting, this is the upper bound you are going to denote. So this you are saying that okay, yes, this is the worst case. So by intuition, actually the big O notation denotes the worst case of your algorithm. If you just say that algorithm A requires order of n square time, or if you just say that algorithm insertion sort algorithm requires, your insertion sort algorithm requires order of n square time, if you say order of n square time, so if you say insertion sort algorithm requires order of n square time, it means you are claiming that this is the worst case time of your insertion sort. Means your claim is that your insertion sort will not run more than this time. So this is the claim. So here so you can see that okay, so you see here this is one of the f of n. Sometimes you may have the f of n like this. You may have the f of n like this. Okay, sometimes you may have f of n like this. Sometimes you may have the f of n like this. Sometimes you may have the f of n like this. This is the f of n. Okay, sometimes you may have the f of n like this, or very slow. You may have the situation like this. F of n may be like this. Now see the situation. So you have the f of n, you have mentioned the g of n. So c into g of n. So see, once you say that this condition f of rate of growth of f of n, if you have the rate of growth of f of n is less than or equal to c into g of n, then you can say that f of n is big O of, you are saying that f of n is big O of g of n. Okay, when you are going to see, when you say that this is the condition, if g of n, you have some g of n, and if f of n is less than or equal to this, so you see that after some value, if you have this f of n is this, then the rate of growth of f of n is always less than or equal to this c into g of n for some value of n0. If you say this f of n, then also it rate of growth of this is less than the rate of growth of c into g of n. So all such f of n, for all such f of n, you can also say that this f of n is big O of g of n. And that's why I'm saying that this denotes the upper bound, but may or may not be tight. So like this, if you have, if g of n is, if you have the g of n, say, if you have some g of n is like this, you may have the some g of n is n square, and you have some, okay, some function f of n. You have some f of n, maybe like this. You have, this is f of n, and f of n, say f of, this may be the f of n. So you have maybe, and this is, so we say that after this value, some value of n0, you have f of n, and you have some c into n square. Here g of n is what? N square. So here n square is, f of n is 5n square plus 10. So rate, if you say that f of n means 5n square plus 10 is less than or equal to some c multiplied by n square, and you need to determine some c for which this relationship holds. And if this is less than or equal to, say you have determined some c, some constant, like c is some constant for which you come to know that 5n square plus 10 is less than or equal to some c into n square, then you can also say that if you have the n into some 1.5 plus 10, some polynomial like this, degree is less than the, here degree is 1.5 and degree is here 2. So rate of growth of, since this is 1.5 and this is n square, this will also be less than or equal to same c n square. And even this is degree of this polynomial is 1, this will also be less than or equal to c into n square. So if this is less than or equal to c into n square, then this will also be less than or equal to this square. This will also be less than or equal to c into n square. And even since the log rate of growth of the logarithm is less than the polynomial, you can also say that log n is also less than c into n square, some for some constant. So you can, so you can, if this condition holds true for representing the f of n with the help of the big O notation, this condition must hold true. If this is true, then you can say that okay, yes, this 5n square plus 10 is what? This is big O of n square. If this is less than or equal to some c into n square, then you can also say for this is the n square. If n plus 100 is less than or equal to some c into n square, you can also say that big O of n square. Here g of n is n square everywhere. And here even you have f of n is log n, then you can say that this is O of n square. Now see that if somebody has analyzed the number of operation and he come up with the number of operations log n, and he is telling that yes, since log n is less than or equal to c into n square, he can say that yes, I can say that log n is big O of n square, because this is the claim, this is the upper bound you are mentioning. You are claiming that this is the maximum time. So with this definition, actually, you are able to tell this also. Since the condition for saying that f of n is big O of g of n is only this, f of n should be less than or equal to some c into g of n. So that's why whenever you have the bound degrees of polynomial is n square, and you are saying that okay, this big O of n square, then this represents the tight bound actually. This is the tight bond. And whenever you say that n is power 1.5 plus 10 is less than or equal to c into n square, and you are saying that big O of n square, this is not a tight bond, because this is the polynomial of degree 1.5 and this is the polynomial of degree 2. Always rate of growth of polynomial of degree 2 is always more than the rate of growth of the polynomial 1.5, and hence and this is always very slow as compared with this. The rate of growth of this is very slow as compared with this. And even this is the linear in nature. So one is linear in nature and one is quadratic in nature. So actually whenever you say like this, then you have the situation actually you are mentioning like this is the uppercase you are mentioning for the n square, but actual uppercase is like this. So since the rate of growth of this is the polynomial of degree 1, but you are representing with the help of big O of n square, and n square is this is the upper bound. But actually this is the linear in nature. You could have say that okay, this is the upper bound, but instead of saying that this is upper bound, you are saying that this n square is the upper bound. And once you say n square is the upper bound, and this is the meaning that this is not a tight bound. And this is, if you have the logarithmic in nature and still you are saying that with the condition only that this is the mathematical condition that log n rate of growth of this function is less than or equal to c into n square. And with this definition actually, because you know that This is the definition for being that f of n is big O of n square, and you just say that this is big O of n square, and these bonds are not tight. So these are the not tight. If you say that if the number of operations required by your algorithm is this, and if you say that this is the big O of n square, then this is not tight. If the number of operations required by some algorithm is n plus 100, and you are saying that this is the big O of n square, this is not tight. Like this. So that's for but by definition, if you have the operations, number of operations required by the algorithm, this is this, and you say that this is the big O of n square, then by definition you can see nobody can stop you. That's why this says that we denote the asymptotic upper bound that may or may not be tight. So what you are actually going to claim here? So here you have the big O of f of n is big O of n. So here once you say that f of n is big O of n, actually you should not mean this equal to sign as the equal sign. This is the abuse of writing the equal sign. Here once you say f of n is big O of so whenever you say f of n is big O of g of n. Okay. So here writing the equal to sign actually in the case of asymptotic notations, here this equal to sign does not mean that this is left side is equal to the right hand side. So LHS is equal to the RHS. This is not the meaning actually. We are not claiming that f of n is equal to this, because what? This f of n is what? F of n is the in one specific function, particular function, where once you are saying that big O of g of n, this represents the set of function. This is a set of function. This is not the one function. So while writing f of n is big O of g of n, actually what you are claiming that the appropriately you can say that f of n belongs to big O of g of n. So this is the actually appropriate way to say. So whenever you are, but in the literature you will find that, later you have already, you will find that this is the equal to sign they have mentioned to mean that you have to read like this: f of n is not, you should not say that f of n is equal to this. You can say that f of n is big O of g of n. You can say like this. So you should not say that f of n is equal to big O of no. You can just say that f of n is big O of this. So once you say like this, it means that you are claiming that f of n is a member of this set, and this is the set of function. This is the set. So this represents this set, and this is the one particular function. This is one particular function. One particular function. So this is one particular function, and you are saying that f of n is big O of g of n. This means you are saying that f of n is a member of this set, and means this is some set, means this is some kind of group. Say for example, we have divided, you might have set some groups, so you are referring some groups. So this is the group, and you are claiming that if you say that okay, this belongs to this group, means you know the behavior of this group, and you know that what is the mix. You don't want to say specific, but you just want to tell that okay, this algorithm belongs to this group, and we know the behavior of this group. Okay? Like one is in our grading system, you know that some students can obtain the A plus grade, some students can obtain the O grade, and we have the notion of A plus or A grade. So when we say that okay, if you have greater than or equal to 90 marks, you are having the O grade. If you have if you have the marks less than 90 but greater than or equal to, say, if you have the greater than or equal to 80, So if your marks is, if you have the marks which is greater than or equal to 80 and you have the less than 90, so you can say that this is the A plus grade. So between 89 89 to either less than or equal to 89, or from 89, sorry, you can say that from 80, from 80, if you have the marks 80 to 89, less than 90, so you will be given, say for example, grade A. If you have the marks 90 to 100, greater than or equal to 90, then 100, then you will be have O grade. So this is just simple. If in some grading system, if somebody has decided this kind of notion, if his students has obtained the marks from 80 to 89, we will say that okay, he will be awarded grade A. Some students have marks 90 to 100, then he will be awarded the grade O grade. Now if some students comes to me and says that okay, I have the 85 marks, then I will say that okay, if you are 85 marks, then you are in the group A. Somebody says that I have 91 marks, so I will say that you are in the group O. And I know the behavior of the group A and group O. So I believe that those having the marks greater than or equal to 90, they have intellectually nature, they can pick up very fast, they are intelligent one, and they can understand the things very quickly. But I have believed that those are in the group A. I know that okay, these students are having the marks between 80 and 89, and they are the above average students. And if for a small direction, they can pick up more. But the students which are in the group O, even they don't require for any direction, they can itself develop. So this is the intuition of the groups. So similarly, in case of the algorithms, whenever you are referring with the help of the asymptotic notation, you are going to denote some particular groups. So here actually you are going to refer the group's name. So you are saying that once you say f of n is big O of g of n, this means you are claiming that f of n is a member of this set, means f of n belongs to this group, and we know the property of this group. So O of g of n, O of g of n, actually this denotes the set of function f of n. This is the set of function f of n such that there exist positive constants c and n0 such that f of n is less than or equal to some c into g of n, and we are saying that f of n is itself more than or equal to 0, and this is for all value of n greater than or equal to n0. This is. So if you have all f of n will come in this group, those satisfy this condition. So that's why whenever you say that f of n is big O of g of n, then the big O of g of n will represent this kind of notation. So big O of g of n is a set, and the all f of n will be in this set. Those are satisfying the condition this. So here f of n is less than or equal to some constant multiplied by g of n. Okay, f of n is less than or equal to some constant multiplied by g of n, and f of n is again greater than or equal to 0. And what we believe that f of n is this is the asymptotically positive functions, and this is also f of n and g of n both are asymptotically positive functions, because just we are counting the number of operations. So that's why whenever in the case of the analysis f of n, whenever we write f of n and g of n, we believe that these are the asymptotically positive, means for sufficiently large value of n, these functions have the positive values. So that's why I'm referring that f of n is greater than or equal to 0. Okay, so this is the notion of the big O notation. See that we say we have the f of n. We have f of n. Say f of n is 5n square plus 10. Now I have counted the operations in my algorithms, and I come to know that my algorithms takes the number of operations like this 5n square plus 10. So now we need to say represent this analysis with the help of the big O notation. But for representing the analysis in terms of the big O notation, we must determine the function g of n, so that you can claim that f of n is less than or equal to c into g of n. So let us say g of n is n square. So let us say we say that we have g of n, and g of n is, say, n square is n square, and n square, we believe that this is the g of n, and we need to select some constant. So say I'm going to select the constant like 6. So this is the value of some constant. Now if f of n is less than or equal to some constant c into g of n, if, and for that actually I need to determine the value of n0, because this says that f of n is less than or equal to some c into g of n for every value of n, for every value of n, for all n greater than or equal to n0. So we need to, we have, say, we have determined some constant, say roughly we have come to know some constant 6, and I need to know that what is the value of n0. After that, this relationship will hold true, because I have already mentioned you that for a small value of n, the relationship may not hold true, but for sufficiently large value of n, this relationship may hold true. So we are going to work on the asymptotic analysis, and we are working for sufficiently large value of n. So see that what should be the value of n for which you can say that this relationship holds true. So if n is equal to 1, you know that if n is equal to 1, if it is n is equal to 1, then f of n, this has value 5 plus 10, this means 15. And I am saying that this is less than or equal to this. So 6 into 1, this is 6, and this relationship is not going to satisfy if n is equal to 1. So, but if n is equal to 2, then you say 4, and 4 times 5 means 20 plus 10, 30. You can say this is the 30, and less than or equal to 2 means 4, 4 times 6, 24. Still, you are not going to satisfy. You are not saying that this is less than or equal to this. But say, roughly I have set n is equal to 5. If n is equal to 5, then what will happen? If n is equal to 5, 5 into 5, 25 multiplied by 5, 125, 125 plus 10, 135, and here how much? 5 means 25, 5 square means 25, and 25 multiplied by 6, how much? This is 150. Now say this relationship holds true. Now if you say more values, say n is equal to 10. So if n is equal to 10, then see what happens. 10 means 100, n square means 100, multiply by 5, 510. Here you will have 510, and here how much? N is 10, 100, 100 multiplied by 6 means 600. This still holds true. To see that situation, after the value, roughly you have come to know, it may be hold for 4 also, but roughly we have come to know that, and this says that there exists a positive constant. There exists. So one positive constant, if you have determined just one positive constant, that will hold, that will satisfy the condition, then it will go through. So you can just, we have seen some c, and for some c you have some value. So depends on the value of c, you will have some n0. So but we don't worry which c and which n0. If there exists, this says that if there exists, we can, means you can find out any c and for that you have to determine is there some n0 exist for which you can say this relation holds true. So we have found the c, we have taken c as 6, and we have found the value of n0 as roughly, we have come to know that this is the 5. So after the value of 5 greater than or equal to, for all n greater than or equal to n0, where n0 is, we have just determined here 5. Roughly, it may hold also for the 4. So, but condition is that after the value of 5, this the relationship always holds true. And definition says that if f of n is less than or equal to, if f of n is less than, this is f of n, is less than or equal to some c into g of n, g of n is n square, or some value of n, for all value of n greater than or equal to n0, then you can say that f of n is big O of g of n. So means this is a member of this set. So big O of g of n is the set, and hence f of n is a member of the set big O of g of n. So you can say that f of n is less than or equal to c into g of n. You have determined the constant c and n0. So by definition, you can say that f of n is a member of which set? Is a member of big O of f of n. And f of n here is what? 5n square plus 10. So once you have the analysis 5n square plus 10, you can just say that this is the order of n square. So this is f of n, and this is g of n. So this is the big O of g of n. So you say that f of n is big O of g of n. Why it is so? Because you come to know this kind of relationship. So this is the way you can determine. So you just need to determine some constant c, and for that you have some value of n0. That's all. Now see that if you take the, so you have come to know that 5n square plus 10 is less than or equal to 6n square. Then you can also say that if you have the 100n plus say 10, this will also less than 6 into n square. And for that actually you may have some n0 may be different, but surely there will be some n0 after which the rate of growth of this is very high as compared with this, means this is less than or equal to this. And if you have the logarithmic in nature, log n, rate of growth of log n is always less than the rate of growth of any polynomial, and hence you can say that this is also less than or equal to 6n square. So if this is less than or equal to this, then since this is less than this, so you can also say that this is less than or equal to this. This is also less than or equal to this. And similarly, you can say log n is also less than or equal to 6 into n square. So that's why if your operation is like this, you can also say that this is O of n square. And once you write like this is not a tight bound. But once you say big O of n square here, and degree of the operation polynomial is 2, and once you say like this, then this is the tight bound you are going to represent. So this is the way. So whenever you are going to use the big O notation, then try to represent the g of n, the maximum g of n, for which the relationship holds true. So f of n, so degree of f of n if 2, then you will come to know that if you are representing with the help of degree 2, g of n is 2, then this is the tight bound. So see that for representing the after the operations, if you have, say for example, 100 n cube plus 100 n plus 50, so you just say that this is the big O of n cube, because actually simply what is the intuition of writing in this? Say you have the 5 n square plus 10, and we have seen that we are writing as big O of n square. And n square is what? This is the highest degree of, this is the degree of polynomial. The rate of growth, this is the constant term, and this is the term which has the degree 2, and this is the coefficient of the degree 2. So this, the rate of growth of this is very high as compared with this. So whenever you go for representing in terms of the asymptotic notation, actually this is the term which has the highest rate of growth. So we are writing actually highest order growth terms. So here the rate of growth of nq is, we know that, very high. So degree of this polynomial is 3 and we just write this is O of nq. And surely you will have some c and n0. If you determine, then you will find some value of c and some value for c and n0, so that you will say that this is less than or equal to this. But you don't worry to determine c and n0 whenever you have, whenever you are going to analyze the algorithm, and if you have the number of operations like this, you just write the highest order growth term. So in asymptotic notation, writing like this, say you have 5n square plus 10 is equal to 6n, so you are writing big O of n square. So you have 5n square plus 10, you are writing big O of n square. If you write like this, big O of 5n square plus 10, this is the poor way of representing. In the asymptotic notation, we don't require to write the lower order term. These are the lower order term. So this is the constant, and this is the coefficient which is the constant. And see, since we are working for sufficiently large value of n, and once you are working for sufficiently large, means n tends to infinite. So once n tends to infinite, then see the lower order terms, they are the constant, and then the lower order terms are dominated by the effect of large value of n. So if say if you have the 10 n square plus 10, so if n tends to infinite, then adding in the amount, adding 10 is nothing, means that for the large value of n, this lower order term is dominated. So lower order term is dominated by the effect of large value of n. Since this is the constant is constant, and this is the coefficient which is also a constant, but this is the variables, and once n tends to infinite, then the rate of growth of this is very high as compared with this, and the lower order terms is dominated by the effect of large value of n. And that's why once you go for the asymptotic notation, you have counted the operations like 5n square plus 10, you just not write the lower order term. These are the lower order terms. You just write big O of n square. So in asymptotic notation, we don't require to write the lower order terms. Theorem says that if you have the polynomial of degree d, this is the polynomial of degree d. Okay. And in these cases, ai's are constants, and what we assume that the ad, which is the coefficient of n raised power d, must be positive. Why it is so? Other coefficients, ad minus 1 or ad minus 2 or a1, a0, they may be positive or negative, but we should ensure that the coefficient ad, which is the coefficient of the n raised power d, must be greater than 0. This we actually, once you are going to tell like this, then we are telling that this is the asymptotically positive functions. And you come to know that once you have the two functions f of n and g of n, and you are saying that f of n is big O of g of n, and here what we have assumed that f of n is positive, asymptotically positive function, and g of n is also asymptotically positive function. So that's why if the coefficient of the highest degree, highest power is positive, then asymptotically this polynomial will be positive. So that's why this is the That's why actually we ensure that the AD must be greater than 0. Then we can say that P of n is big O of n raised power d. This we need to prove. So if you can prove this theorem, then later on whenever you have some polynomial, you just see what is the highest power, means what is the degree of this polynomial, and just write in the terms of big O notation. You just say that P of n is big O of n is power d. You don't require to determine the value of C and n0. So whenever you say P of n is big O of n is power d, how can you prove? So whenever you say P of n is big O of n is power d, we are supposed to prove. We need to prove. Okay. To prove, we need to prove like this. If you want to prove, then what you need to do? Actually, you need to determine. Then you need to determine that P of n should be less than or equal to some constant, some positive constant C, and times nd for every value of n greater than or equal to n0. So once you want to prove that P of n is big O of n is power d, this means you need to prove that P of n will be less than or equal to C times n is power d for every value of n greater than or equal to n0. Now actually you need to determine what will be the C and what will be the n0. You need to determine. And in general, if you have determined, then later on you don't require to determine for a specific polynomial. You just write the in terms of the big O notation with the degree. So how we can prove it? So here P of n is what? Here we have the P of n, and P of n is what you are having. P of n is simply say that you have AD n is power d plus AD minus 1 n is power d minus 1 plus, say, you have the A1 n is power 1 plus A0 n is power 0. So I is equal to 0 to d. So I is equal to 0 to d. So this is the polynomial we have. So in order to prove, we need to determine, actually we need to determine the C and n0. This is our target. So how can you prove that? Can you say, now you have seen that AD is positive. AD is only positive, whereas AD minus 1, AD minus 2 up to AN, A1 or A0, they may be positive or negative. We don't know. But we know only that AD is positive. So can you say this is less than or equal to AD, and if you take the absolute value D plus AD minus 1, you can take absolute value n is power D minus 1 plus A1, you can, and plus A0. So see what we have done only, we have just taken the absolute value of the coefficient. So this may be positive or negative, we don't know. A1 may be positive or negative, we don't know. A0 may be positive or negative, we don't know. So if you make every coefficient positive, then this value may be more if all are positives. AD minus 1, A1 up to A1 and N0, if all are positive, then this and this will be same. But if someone is negative, then this will have the more value as compared with this. So that's why you can say that P of n is less than or equal to this. Now you can take, we are interested for the n is power d, so you can take n is power d outside. So this can be written as this is equal to what? We just take n is power d outside. So you have just ad, and this is the absolute value, plus what we are going to do? We are going to take n is power d outside. So n is power d we have taken outside. So ad, only here ad you will have, and here you will have what? ad minus 1
upon n.
upon n. Good. Then if you have the ad minus 2 upon, what will you have?
n square.
N square. है ना? So like this, if you go up to a1 divided by n is power d minus 1, yes or no? This is a1. Are you clear this? Because a1 times n, and you have taken n is power d outside. So here what? a1 divided by n is power d minus 1. Are you getting this thing?
Yes, sir.
है ना? And here if you have the a0, then this divided by n is power d. Are you getting this thing or not?
Yes, sir.
Simply we have taken n is power d outside. Okay, clear?
Yes, sir.
So now see, we can write this is equal to this. Now can you say this and this are same? So can you say this is less than or equal to ad plus ad minus 1 plus a1 plus a0 and n is power d for all n greater than or equal to 1. So can you say this is this is less than or equal to this? If n is equal to 1, if n is equal to 1, then this and this will be same. Are you getting?
Yes, sir.
If n is equal to 1, then this and this will be same. If n is equal to more than 1, then this will have less value as compared with this. Are you getting?
Yes, sir.
Okay. So now we have come to know that p of n is less than or equal to absolute value of ad plus absolute value of ad minus 1 up to absolute value of a1 and a0 times n is power d. Now this is positive, no? You know this is also a positive, this is also a positive because we have taken the absolute value. So instead of writing this, you just write the constant c, which denotes c is equal to what? And we know that in the definition c is the positive constant, and here c is equal to what? C is equal to absolute value of ad plus absolute value of ad minus 1 plus and so on, plus it will go up to absolute value of a1 plus absolute value of a0. So c is equal to actually this, and you just write n is for d, and this. So here actually you come to know that now actually you come to know that p of n is less than or equal to c into n is power d, and this is holds true for every value of n greater than or equal to 1. You have seen that this is true for every value of n greater than or equal to 1. So see that where if this is true, then you can say that p of n is big O of n raised power d. So you have proved that P of n is big O of n raised power d, and what C is there? C is equal to actually AD plus AD minus 1 plus A1 plus A0, and here N0 you have determined as equal to 1. So you have determined C and N0, for which you have proved that P of n is less than or equal to C times n is power d, where C is positive constant because this is the positive value. And this will hold true for every value of n greater than or equal to 0. And by definition, once you have this kind of situation, if P of n is less than or equal to C into n is power d, here n is power d is the g of n and this is the f of n like this. So P of n is big O of n is power d. This is the proof. So we have the proof. So now you have proved that if you have the polynomial of degree d, then if you have the polynomial of degree d, then you just say that P of n is big O of n is power d. You don't require actually to determine the what should be the value of C, what should be the value of n0. It will hold. So whenever you have the equations like this, some algorithm B has the operation f of n, and f of n is 100 n is power say 110 plus 300 n is power 5 plus say for example 100 n is power 2 plus say for example this is. Now you don't worry to determine the value. This is the say these are very large, somewhat large coefficients, and this is the constant which is sufficiently large. So don't waste your time to determine what should be the C and N0. You just say that there will be some C and N0 for which you can say that f of n is. So what you need to say, what is the degree? Highest degree of this polynomial is what? This is the n is power 10. So simply you can say that f of n is big O of n is power 10. You don't require to determine C and N0. Whenever you have come up with the operations like this, you have the algorithm B, and you come to know that algorithm B you did the analysis, and on analysis you come to know that f of n will take the algorithm B will take the operations 100 n is power 10 plus 300 n is power 5 plus 100 n square plus something like 100,000. So you don't waste your time to determine the C and N0, because we have the proof the theorem there will be some C and N0 for which the relationship holds true, and hence simply you say that f of n is big O of n is power 10, because highest degree of this polynomial is 10. And what is the intuition actually? Intuition is that this is one term you have, this is other term you have, this is the constant term you have, and you know that rate of growth of constant term is always less as compared with the polynomials. Rate of growth of polynomial of degree 2 will be less than the rate of growth of polynomial of degree 5. Rate of growth of polynomial of 10 is less than the degree 5. So this term has the highest rate growth. N is power 10 has the highest rate growth as compared with. So n is power 10, the rate of growth of n is power 10 will be more than n is power 5. So this is the highest rate growth term, and just you have mentioned the highest rate growth because the for sufficiently large value of n, this will be very large, and this large amount will dominate the effect. The the values these values are dominated by the effect of large value of this, because once n tends to infinite, the rate of growth of n is power 10 is very high, and this will dominate the effect of this. These are the lower order terms. So that's why by intuition actually whenever you have come to know with some sort of operations, some sort of operations in terms of the polynomial, you just say that what is the highest degree of this polynomial, and you just need to write the highest degree. Now, if you have the mix up like this, if you have f of n, if you have the f of n is 2 raised power n plus 100 n cube plus 100 n plus 5, like this. So intuition is same. Here, here the actually this is not the polynomial actually. This is what? This is the exponential behavior actually. So highest rate of growth is this. 2 raised power n has the highest rate of growth. So you what you need to say? You once you have the operations in this form, then you just say that f of n is big O of 2 raised power n. Just you don't require to determine c and n0. There will exist. It is so because 2 raised power n is the term that has the highest rate growth among every terms. N is power 3 or n are constant. Okay. So whenever you have the operations, you just write like this. So you know that f of n, once you say f of n is 2 raised power n plus say 100 n cube plus 100 n plus 5. You can also write like this 2 raised power n plus big O of n cube. So asymptotic notations can also be used within the expression. So see, for representing this, if you don't say what it denotes, this denotes the worst behavior of this group. And you know that once you have the degree 3, the n is power 3, then what is the, in this set, you know that all polynomials of degree d, whose degree is less than or equal to 3 will be here. So f of n, all f of n will be is here, who has satisfied the condition c into n is power 3. So here f of n must have degree either 3 or less than 3. So here all polynomials of degree less than or equal to 3, greater than or equal to 0 will be here. So worst case is what? So once you are writing like this, once you are writing big O of n cube, you don't want, here actually a specific function is this. This is the specific function, particular function. But if you don't want to name this specific function, you just say that okay, you are, once you say big O of n is power 3 means you are referring some anonymous function. And you don't want to name this function, as you know that your intuition is that to denote that whatever the polynomial is here, the worst case behavior is this. So you don't want to name the particular. This is the worst case behavior, means in worst case the degree of polynomial here is 3. And you know that 2 raised power n has the highest rate growth over this. And finally you can say that this is big O of 2 raised power n. So asymptotic notations can also be used within the expression. But you have to know the intuition. So whenever you are writing the asymptotic notation, every time you write the asymptotic notation, you are referring some anonymous function. So if you say that 3n square plus 5n plus 10, you can say like this 3n square plus big O of n. So you have written big O of n. This means you are writing some anonymous function which is have the maximum degree is 1. This is more general. You can say like this, instead of, you can 3n square plus 5n plus 5n plus, you can say this is order of 1. And you know that once you have written order of 1, so here you should not mean 1 as the 1 minute or 1 second or 1 operations. No, simply 1 denotes that this is the constant. So this is the independent of the input size. So whatever be the value of, whatever be the input, you don't worry, you have this some constant. So this refers some constant value, and you don't want to, because you know that constants are constant, rate of growth of constant is always less than the polynomial. So you don't want to refer the specific constant, you just refer the you are referring the anonymous function, which is the constant. And in this way you can 3n square plus, you can write this as big O of n, and then finally you can say that this is big O of n square. So whenever you are writing big O of 1, this is the constant. You are referring the constant time. So constant time you are going to refer with the help of big O of 1. Means it does not depends on the value of input size. This is some constant. You don't want to name, you don't want to use some, you don't want to specify the specific one. You say that okay, yes, there is some constant here. Okay. So if you have some polynomial, if you have some algorithm, and if you come to know that algorithm A, the behavior of algorithm A is order of 1, then this is excellent one, because we try to write the algorithm that is independent of the input size. If it is so, then whatever be the input, we don't worry. You can run the algorithm for sufficiently large value, maybe n tends to infinite, you will be able to run, because you always take the constant time, same amount of time. Whatever time you need for one value, you will take the same time for the 10 values or 500 or 1 million. So this is the constant. So our intuition is to write the algorithm. We need to devise the algorithm so that it should come, its time should be constant, but it is very difficult to achieve. So, but most of the time, what we need to say that we should try to write the algorithm whose behavior is polynomial, and polynomial n is power d. Once I say n is power d, this is the polynomial, and this degree, whenever I say you have some n is power d, this is the polynomial in time. So we can say that the algorithm runs in the polynomial time, because n is power d is the polynomial of degree d. But here d should, your d, what we expect that your d should be less than or equal to 3. Then you will be able to trace the output for sufficiently large value of n. But once d is sufficiently large, say if d is equal to 100, then even n is power d, even this is the polynomial time algorithm, but since degree is very large, and it is just like the exponential actually. This is very large. Very soon your algorithm will go to the, will take many infinite, it, it will go to interactable actually, and for sufficiently large value of n, you may not able to find the output of such algorithm. So what we expect that even the degree of your polynomial, your algorithm, once you analyze your algorithm and you come up with that the degree as polynomial, the degree of polynomial means we should have the degree up to 3. Once you have the degree more than 3, then your algorithm is going to enter in the super polynomial time. So your algorithm will go enter to the super polynomial time. If you have the d degree which is greater than 3. So and once your algorithm is in the super polynomial time, this means you are also taking sufficiently large operation, and when input size is large, your algorithm may not produce any kind of output. It may be busy with the computation, and your algorithm, your program, it will become intractable. So our target is to write the algorithm that should have the smallest value of degree. So we try to prefer to write the constant time algorithm. If not possible, we need to go for the polynomial time algorithm or logarithmic time in nature. Or we try to avoid writing the algorithm which is exponential in nature. So exponential in nature means whenever you have some constant a raised power d, a is constant. So a is what? A is constant. A is constant greater than 1, and okay, so just like, and you have some d is the variable, then you say that like 2 raised power d, or a can be 3 raised power d, or a can be 4 raised power d, and d can be anything. So this is the exponential in nature. So simply some constant raised to the power variable terms. This is the exponential in nature. So try to avoid writing the algorithm that is exponential in nature. But unfortunately, many problems in computer science have the nature exponential. And that's why the intuition of the design and analysis of algorithm is to we need to devise some techniques using that you can write formulate the problem solution of the problem so that you should be able to solve that problem in reasonable amount of time. The problem whose behavior is exponential in nature, whose behavior is even more than exponential, say factorial. Some problems may have the complexity of big O of factorial 1, big O of factorial n. And once you say big O of factorial n, this is also more than the exponential actually. So this is also a very large amount. So the problem, our the intuition of this course is to devise the algorithm that has behavior either exponential or they are running in the order of factorial n. So we need to devise the techniques so that you can formulate the solution of such problems for which you will be able to find the response in some reasonable time for sufficiently large input size. But in many problems in computer science, we will come to know later on that their behavior is exponential and very soon the problems becomes intractable. You are not getting any response for sufficiently large input size. And such problems in the next we will see that the such problems are known as computationally hard problem in computer science. So this is the intuition of the big O notation. Actually, the same kind of intuition you have to use for other asymptotic notation. Just big O notation denotes the asymptotic upper bound by intuition, and some other notation will have some different meanings. If you, sometimes you will say that your algorithm belongs to 2 raised power n. Sometimes you say that my algorithm belongs to log n time, like binary search algorithm, log 2n. Sometimes you say that my algorithms in the n order of n square. Sometimes you will come to know that my algorithm is order of n cube. Sometimes you may say that my algorithm is order of n cube. So if you say that algorithm A, the running time of algorithm A is big O of 2 raised power n. Running time of algorithm B is big O of log n. Running time of algorithm C is big O of n square. Running time of algorithm D is big O of n cube. Running time of algorithm E is, for example, big O of factorial n. So what you are telling actually, you are representing, you are telling that okay, this your algorithm comes in this group, and you know the nature of this group. If your algorithm comes in order of 2 raised power n, then we know that very soon your algorithm will enter to the infinite group. If your algorithm comes in the log n group, big O of log n, then you know that for sufficiently large value of n, you will be able to find the response. And this is also somewhat okay. And once you have your algorithm in this group and you know the nature of this group, and you come to know that very soon your algorithm will enter to the it will go for the execution of infinite instructions, and the problems becomes intractable. So this is the behavior. So once you say that okay, my algorithm is order of factorial n, somebody say that my algorithm comes in the order of n cube, somebody says my algorithm is order of n square, or some says that order of log n, order of 2 raised power n. Then all algorithms if all algorithms are solving problem x, if all algorithms are solving problem x, so A is also the algorithm, A is solving the problem x, B is, someone has written the algorithm B for solving problem x, someone has the algorithm C for x, someone has D, someone has E. So among these available, these available algorithms, which one will we will prefer? We will prefer this algorithm. Means we will prefer the algorithm B because its behavior is what? Order of log n, because we know the nature of this group and the rate of growth of log n is very is small as compared with. So you may have the factorial of n maybe like this. Okay, 2 raised power n may have 2 raised power n. You may have some quadratic n square. Okay, you may have some nq, and you have some maybe some log n. So no, you know that the rate of growth of the rate of growth of log n is always less than this. So that's why we need to prefer the algorithm that has the which is the among these which is the having the time order of log n, because with the intuition that we are working for sufficiently large value of n, and for sufficiently large value of n the algorithm b will run fast as compared with other algorithms, and you will be able to find the response for sufficiently large value of n. So this is actually the intuition of notations. So whenever you are going to use the asymptotic notation, with the help of the asymptotic notation, you are just telling the group name where your algorithm falls. And people know that the behavior of the group name.